Late 1940, Air Ministry Headquarters, London. Rain hammered against blackout curtains as senior engineers reviewed American blueprints for a 2,200 horsepower aircraft engine. "Impossible," declared Chief Engineer Roland Pemberton, circling the specifications in red ink. "The metallurgy doesn't exist. The cooling systems will fail. They're chasing fantasy whilst we're fighting a war." His colleagues nodded. Britain's own Merlin engines, magnificent at 1,200 horsepower, represented the practical ceiling, anything beyond courted catastrophic failure. But across the Atlantic, American engineers had already begun building what the British deemed unfeasible, and that engine would change everything. 23rd September 1940, 14:47 hours. The Rolls-Royce facility in Derby operated under perpetual twilight, its windows painted black against Luftwaffe reconnaissance. Inside, the air tasted of machine oil and desperation. Wing Commander James Hartley stood before a disassembled Merlin engine, its components spread across steel tables like a mechanical autopsy. Outside, the distant rumble of anti-aircraft batteries punctuated the afternoon shift. Britain's aviation engineers faced mathematical brutality. The Merlin XX, producing 1,280 horsepower, represented the zenith of British engine development, a marvel of precision engineering that powered Spitfires and Hurricanes through the summer's desperate fighting. Each engine required 6,000 man-hours to build. Britain produced roughly 3,000 monthly, cannibalizing every available machine shop, training semi-skilled workers in precision tolerances, stretching supply chains already strained by U-boat warfare. The physical limitations were unforgiving. Cylinder temperatures in the Merlin reached 2,400 degrees Fahrenheit at maximum power. Aluminium alloys, carefully refined through years of metallurgical research, approached their structural limits. Cooling systems demanded intricate glycol circulation through precisely machined passages. Superchargers compressed intake air to 10 pounds per square inch, requiring components machined to tolerances of 0.001 inches. Every increase in power demanded exponentially more sophisticated materials, tighter tolerances, more complex cooling, more robust structures. Hartley possessed intimate knowledge of these limitations. 38 years old, educated at Imperial College London, he'd spent 15 years in aero-engine development. His hands bore scars from test stand accidents. His hearing suffered from proximity to engines running at combat power. He understood viscerally what metal could withstand and where physics imposed non-negotiable boundaries. The American proposal arrived via diplomatic pouch in August 1940. Wright Aeronautical Corporation planned an 18-cylinder radial engine producing 2,200 horsepower, intended for a bomber called the Superfortress. The specifications seemed divorced from engineering reality. That much power from reciprocating pistons required cylinder pressures that would fracture conventional materials. Heat generation would overwhelm any practical cooling system. Vibration harmonics would tear the engine apart within hours. Hartley assembled Britain's foremost engine specialists in a windowless conference room beneath the factory floor. Blueprints covered every available surface. Chief metallurgist Dr. Eleanor Carstairs, who'd pioneered high-temperature alloy development at Cambridge, examined the cylinder specifications through wire-rimmed spectacles. "The thermal expansion alone presents insurmountable problems," she stated flatly. "At these temperatures, aluminium's structural integrity collapses. They'd need materials that don't exist." Squadron leader Thomas Blackwell, responsible for operational engine reliability, studied the cooling system diagrams. Conventional glycol cooling cannot possibly dissipate this heat load. The radiators would need to be twice the size of anything currently flying. The additional weight negates any performance advantage. His fingers traced cooling passages through the complex blueprints. They're designing failure mechanisms, not power plants. The group spent 3 days analyzing every aspect: crankshaft stresses, bearing loads, fuel consumption rates, maintenance intervals, manufacturing requirements. Each analysis reinforced the same conclusion. 2,200 horsepower exceeded practical boundaries. Britain's industrial base, even working at maximum capacity, couldn't produce the precision components required. The specialized steels needed weren't available. The testing infrastructure didn't exist to validate such radical designs. Hartley authored the official response himself, 27 pages of detailed technical analysis. "While we appreciate American enthusiasm," he wrote diplomatically, "fundamental physical and metallurgical constraints render this specification unachievable within operational requirements. We recommend focusing development resources on proven designs capable of incremental improvement." Britain's experience demonstrates that 1,500 horsepower represents the practical ceiling for reliable, maintainable combat engines using available materials and manufacturing capabilities. The assessment reflected not pessimism, but hard-earned realism. British engineers had pushed aviation technology through 2 decades of development. They'd built engines that could run 300 hours between overhauls, survive combat damage, operate in North African heat and Russian cold. This knowledge came at tremendous cost. Test pilots killed in crashes, prototypes that disintegrated, thousands of design iterations, millions of pounds invested in research that yielded incremental gains. The American response arrived 6 weeks later. It consisted of 2 words: watch us. November brought darker news. The Blitz intensified. Coventry's aircraft factories burned. Liverpool's docks suffered catastrophic damage. U-boats ravaged Atlantic convoys. Britain's industrial output, miraculous though it was, couldn't keep pace with losses. Fighter Command needed more Spitfires. Bomber Command needed heavier aircraft to strike Germany. The Royal Navy needed everything. Hartley worked 18-hour shifts. Sleep came in 2-hour intervals on a cot beside the test stands. His wife and daughter had evacuated to Yorkshire. He received letters weekly, his daughter's careful handwriting describing rural life, deliberately cheerful. He kept them in his desk drawer, reading them during rare, quiet moments, reminding himself why precision mattered, why every engine had to work perfectly, why British engineering tradition demanded absolute reliability. The Americans, he learned through intelligence channels, had actually begun building their impossible engine. Reports described massive facilities in Cincinnati, workforce numbering thousands, production techniques that prioritize speed over traditional precision. The cultural contrast was stark. British engineering emphasized craftsmanship, individual skill, time-tested methods. American industry favored mass production, interchangeable parts, standardization, accepting higher failure rates in exchange for volume. Hartley couldn't decide if the Americans were admirably ambitious or dangerously naive. Perhaps, he reflected, both. Britain didn't have the luxury of experimentation. Every engine produced had to work immediately, reliably, without extensive testing. Lives depended directly on quality. The margin for error had vanished somewhere over Kent in September. As 1940 ended, Hartley stood at his drawing board, refining improvements to the Merlin. Incremental gains, better supercharger efficiency, improved fuel injection, strengthened crankshafts. Each modification might add 20 horsepower, extend service life by 50 hours, improve reliability by 2%. Unglamorous work, essential work, British work. Across the Atlantic, American engineers were attempting something that defied everything Hartley knew about aviation power plants. He hoped, despite his professional skepticism, that they might succeed. Britain needed every possible advantage, but hope, he'd learned, wasn't engineering. Physics was. And physics, he believed, would prove him correct. March 1942, 06:15 hours. Spring dawn broke grey over Derby, revealing factory rooftops scarred by incendiary damage. Hartley walked through the facility where 4,200 workers maintained continuous production across 3 shifts. The noise was overwhelming. Lathes spinning at 3,000 RPM, hydraulic presses stamping crankcase components, grinding wheels shaping cylinder heads. test stands running engines at full power, quality inspectors shouting specifications over the mechanical thunder. Production demands had intensified impossibly. The Air Ministry required 4,500 Merlins monthly. That number represented not merely engines, but tens of thousands of precision components. Camshafts machined to zero. You drove 5-inch tolerances, pistons hand-fitted to cylinders, connecting rods balanced to within grams, supercharger impellers requiring 20 hours of individual finishing. Each engine contained approximately 18,000 parts, every one critical, every one requiring inspection. The workforce transformed radically. Skilled machinists, previously taking 5 years to train, were now supplemented by hastily trained civilians. Women comprised 40% of workers, many previously employed as shop assistants, teachers, domestic servants. They learned precision measurement, blueprint reading, metallurgical properties. Instructors condensed 5-year apprenticeships into 12-week crash courses. Standards couldn't drop. Engines either worked perfectly or pilots died, so inspection became fanatically rigorous. Material shortages created constant crises. Aluminium alloys required imports from Canada and Australia, vulnerable to U-boat interdiction. High-grade steel came from Sweden through increasingly dangerous routes. Magnesium, essential for lightweight components, was perpetually scarce. Procurement officers requisitioned materials through labyrinthine bureaucracy, trading priorities with other ministries, always negotiating, always compromising, making impossible decisions about which critical projects received limited resources. Dr. Carstairs led materials research in a laboratory that occupied converted storage rooms beneath the main factory. Her team of 6 metallurgists worked with antiquated equipment, improvising constantly. They analyzed failed engine components, identifying stress fracture patterns, recommending alloy modifications, testing alternatives when primary materials became unavailable. Every improvement required extensive validation. Engines couldn't fail experimentally in combat. "We're approaching theoretical limits," Carstairs explained to Hartley during a midnight inspection. She held a fractured connecting rod, its surface revealing crystalline failure patterns under magnification. "Aluminium alloys can't withstand higher compression ratios. We've refined grain structures, optimized heat treatment, but atomic bonds have absolute strength limits. Physics doesn't negotiate." Hartley understood completely. British engineering tradition emphasized understanding fundamental constraints, working within them cleverly, extracting maximum performance through refinement rather than brute force. This philosophy yielded the Merlin's legendary reliability. Pilots trusted these engines absolutely because they failed predictably when maintenance intervals were exceeded, not randomly during combat. News from America arrived sporadically. Intelligence reports described Wright Aeronautical's struggles with their R-3350 engine. Early prototypes experienced catastrophic failures, cylinder heads cracking, exhaust valves burning, superchargers disintegrating, fires erupting during test runs. Failure rates exceeded 70%. The Americans responded characteristically. They accepted losses, built more prototypes, tested variations simultaneously, threw resources at problems until solutions emerged. The cultural difference fascinated Hartley. British engineering couldn't afford such profligacy. Every test engine represented materials desperately needed elsewhere, man-hours diverted from production. Facilities that could build operational units instead of experimental prototypes. Britain's survival depended on efficiently converting limited resources into reliable weapons immediately. The American luxury of extensive experimentation seemed almost offensive. Yet reports indicated the Americans were making progress. By mid-1942, they'd achieved 1,800 horsepower in sustained testing. Failure rates dropped to 40%. New cooling systems using pressurized oil demonstrated promise. Cylinder heads machined from exotic alloys showed improved temperature resistance. They were learning, systematically eliminating failure modes, approaching their impossible goal through sheer persistence. Blackwell returned from a liaison visit to America in July 1942. He'd spent 3 weeks at Wright Aeronautical Facilities in Cincinnati, observing their development process. His report was extensive, grudgingly admiring, deeply unsettling. "Their industrial scale is incomprehensible," he told Hartley over weak tea in the office that doubled as sleeping quarters. "Single factories larger than our entire Derby complex, machine tools numbering thousands. Workforce turnover they simply absorb through continuous training. They're industrializing engineering itself." "But the quality," Hartley pressed. "Initially, poor by our standards. 50% of components failed first inspection." Blackwell stirred his tea thoughtfully. "They respond by building more, inspecting everything multiple times, accepting waste as inevitable. Their metallurgists aren't necessarily better than Carstairs, but there are 20 of them working simultaneously on different alloy variations. When they encounter problems, they don't refine existing solutions. They try completely different approaches until something works." The implications troubled Hartley deeply. British engineering philosophy centered on getting things right initially, avoiding waste through careful planning, respecting materials, valuing craftsmanship. The American approach seemed almost wasteful, yet it was undeniably producing results. They'd tackled a problem British experts had deemed impossible and were systematically solving it through brute force experimentation that Britain couldn't afford. Production pressures meanwhile intensified beyond sustainability. Workers collapsed from exhaustion. Accident rates climbed despite safety protocols. A fire in September destroyed an entire assembly hall, killing 11 workers and setting production back 3 weeks. Hartley attended the funerals, standing in rain at suburban cemeteries, watching families bury husbands and sons, knowing that production demands wouldn't decrease, that more workers would die from exhaustion and accidents, that this grinding attrition was Britain's reality. By December 1942, reports confirmed the Americans had achieved 2,000 horsepower in sustained testing. The R-3350 still suffered teething problems, overheating, excessive oil consumption, maintenance intervals too short for operational use. But it ran. It produced power that British engineers had calculated was impossible. Hartley requested the detailed technical documentation, spending weeks analyzing their solutions. They'd bypassed limitations through approaches that Britain hadn't seriously considered. Exotic chromium steel alloys that Britain couldn't produce in quantity. Cooling systems using pressurized oil circulation that required complex pumps. Fuel injection systems demanding precision manufacturing beyond Britain's current capabilities. Cylinder fins machined to dissipate heat more efficiently. Magnesium crankcases that were lighter but terrifyingly flammable. Each solution required resources Britain lacked. The Americans could throw money, materials, facilities, personnel at problems until they yielded. Britain was optimizing existing capabilities, squeezing efficiency from constrained resources, performing engineering miracles within brutal limitations. Both approaches were valid, both were necessary. But Hartley felt, for the first time, that British pragmatism might have caused them to dismiss possibilities that more abundant resources could actually achieve. June 1944, 17:30 hours. Hartley received a telegram marked Priority Ministry Classification. The message was succinct. R-3350 operational. B-29 Superfortress bombing Japan. Presence requested RAF Bovingdon for evaluation. Transport arranged. The flight to Bovingdon occurred on a Lancaster. Hartley strapped into the navigator's position, experiencing viscerally the environment his engines powered. The Merlins roared reliably, their familiar rhythm comforting. The 4-hour flight provided time for reflection. The Americans had done it. They'd built the impossible engine, installed it in the largest bomber ever produced, and deployed it operationally. British skepticism had been definitively disproven. Bovingdon's airfield hosted a single B-29 on detached evaluation. The aircraft dwarfed everything around it. Wingspan 141 feet, length 99 feet, 4 massive radial engines, polished aluminium skin gleaming in afternoon light. Ground crew surrounded it like priests attending some technological deity. Hartley approached slowly, engineering appreciation overcoming professional chagrin. The R-3350 duplex Cyclone radiated brutal power. 18 cylinders arranged in 2 rows, each cylinder displacing 201 cubic inches, compression ratio 6.85.1, twin superchargers forcing air through complex induction systems. The engineering was simultaneously crude and sophisticated, massive compared to the elegant Merlin, yet incorporating solutions that British engineers hadn't seriously pursued. Major Robert Henderson, USAAF liaison, conducted the briefing. 32 years old, Cornell-educated engineer, he displayed the confident enthusiasm that Hartley now associated with American technical personnel. "She's not perfect," Henderson admitted cheerfully. "Overheating remains problematic. Maintenance intervals are half what we'd prefer, but she produces 200 horsepower reliably enough to bomb Tokyo from the Marianas. That's 3,000 miles round trip, carrying 10 tons of ordnance." The numbers were staggering. The entire B-29 represented capabilities beyond British current aircraft development: pressurized cabin for high-altitude operations, remote-controlled gun turrets, radar bombing systems, range exceeding anything in British service, and at the center, 4 engines that British engineers had calculated couldn't exist. Hartley spent 3 days examining the installation. He attended engine startups, hearing the R-3350's distinctive roar, watching mechanics perform maintenance, reviewing technical documentation that filled filing cabinets. The Americans shared everything generously, perhaps not realizing how their openness contrasted with British institutional secrecy. The engine's cooling system was revelatory. Instead of conventional glycol circulation through radiators, the R-3350 used pressurized oil circulation through complex passages machined directly into cylinder heads. Oil temperatures reached 240 degrees Fahrenheit, requiring heat exchangers using airflow from propeller wash. The solution was mechanically complex, requiring pumps and pressure regulators that British designs had avoided, but it worked within the massive cowling that American structural design could accommodate. Metallurgy represented the crucial breakthrough. American steel mills produced chromium-molybdenum alloys in quantities that Britain couldn't match. These exotic materials withstood temperatures and pressures that fractured conventional alloys. The Americans treated these advanced materials as standard components, while British engineers regarded them as precious experimental substances reserved for special applications. Dr. Margaret Sutherland, Cambridge-educated metallurgist attached to British technical intelligence, joined Hartley for detailed examination. She analyzed cylinder head samples using portable spectrographic equipment, mapping alloy compositions. "They've industrialized advanced metallurgy," she observed quietly. "We develop exotic alloys in laboratories. They're producing them in mills measured by acres, rolling thousands of tons monthly. The engineering isn't necessarily superior. It's the scale that's transformative." Hartley watched a B-29 engine start sequence. The massive propeller rotated slowly during hand-cranking, compressed air building pressure, igniters sparking, fuel injection precisely timed. The engine coughed, cylinders firing irregularly, then caught with a thunderous roar that physically vibrated the ground. Smoke erupted from exhausts before clearing. The engine settled into a lumpy, idle 18 cylinders firing in precise sequence. 2,200 horsepower contained within magnesium and steel. Henderson stood beside Hartley, shouting over the noise. "We lost 47 B-29s to engine failures during testing. Crews died perfecting these systems. The R-3350 has probably killed more American airmen than enemy action." His grin was paradoxically cheerful. "But we kept building, kept testing, kept fixing problems until she worked well enough." That statement crystallized the philosophical divide. British engineering couldn't accept such casualties during development. American industry absorbed losses that would cripple British programs, treated failures as inevitable data points, maintained development velocity regardless of setbacks. Neither approach was morally superior. Circumstances dictated methods. The implications extended beyond engines. The B-29 program cost $3 billion, exceeded the Manhattan Project's budget, employed 100,000 workers across multiple states. That single aircraft development program consumed resources equal to Britain's entire annual aviation budget. The Americans were fighting a fundamentally different war, one where industrial capacity became a weapon as devastating as any bomb. Hartley attended a B-29 demonstration flight. The bomber lifted ponderously, requiring the entire Bovingdon runway, but once airborne, it demonstrated capabilities that redefined strategic bombing. Ceiling 31,000 feet, beyond effective anti-aircraft range. Speed 350 miles per hour, faster than most fighters. Range enabling operations from distant bases. The aircraft represented not incremental improvement, but transformative leap. Yet British engineering had contributed invisibly. American metallurgists had consulted Carstairs' published research on high-temperature alloys. British supercharger development influenced R-3350 induction systems. RAF operational experience informed B-29 defensive armament. The collaboration was real, if unequal. Britain provided theoretical foundation and operational wisdom, while America contributed industrial might and willingness to accept developmental risks. During the return flight to Derby, Hartley contemplated lessons learned. British engineers hadn't been wrong to declare 2,100 horsepower unfeasible. They'd correctly assessed Britain's capabilities and constraints. The Americans hadn't proven British engineering incompetent. They demonstrated what unlimited resources and risk tolerance could achieve. Both conclusions could coexist truthfully. May 1945. The European War ended with German surrender. The Pacific War continued with undiminished ferocity as B-29s incinerated Japanese cities with incendiary raids that killed hundreds of thousands, demonstrating strategic bombing's terrible maturation. The R-3350 engines that British engineers had deemed impossible powered every mission, their thunder delivering destruction that made invasion unnecessary. Hartley attended the Technical Debriefing Conference at Farnborough in July 1945. Officers and engineers from Britain and America gathered to assess wartime aviation development, sharing lessons learned, analyzing successes and failures. The atmosphere mixed professional camaraderie with exhausted relief. The war was ending. They'd survived. The conference revealed how deeply Allied engineering had intertwined, despite cultural differences. British research on high-octane fuels enabled American engines to achieve power ratings that conventional fuel couldn't sustain. British development of jet engines, though not directly related to the R-3350, had pushed theoretical boundaries that informed American thinking. American mass production techniques would transform British post-war industry. Each nation had contributed uniquely, compensating for the other's limitations. Statistics presented were overwhelming. America produced 297,000 aircraft during the war. Britain produced 131,000. Combined Allied production exceeded Axis output 3-1. The industrial mobilization represented history's greatest concentration of engineering resources, transforming civilian economies into weapons factories that operated continuously for 6 years. The R-3350 program alone consumed resources exceeding Britain's entire pre-war aviation budget. Yet that single engine enabled strategic bombing that shortened the war, saving countless lives ultimately. The calculus was brutal, but clear. American willingness to spend enormously on development, accepting high failure rates and casualties during testing, produced capabilities that prevented greater losses during invasion operations. Hartley reconnected with Henderson during the conference's social functions. Over whiskey in Farnborough's officers' mess, they discussed their respective experiences candidly. "Your initial assessment was correct," Henderson admitted. "We couldn't have built the R-3350 using British constraints. We required industrial capacity to waste materials, test multiple approaches simultaneously, absorb failures. Without that luxury, your caution was entirely rational." "But you succeeded where we said you'd fail," Hartley replied. "That suggests British engineering had become too cautious, too focused on constraints, insufficiently imaginative about possibilities." Henderson considered thoughtfully. "Or perhaps both approaches were necessary. Your Merlin engines were masterpieces of efficient design, reliable, maintainable, producible within limitations. We built the R-3350 because we had resources to throw at problems until they yielded. Different circumstances, different solutions, neither approach is universally superior." Post-war analysis revealed the R-3350's troubled operational history. Engine failures caused 147 B-29 losses during combat operations, killing over 1,100 American airmen. Maintenance requirements were horrendous. Complete engine changes every 75 hours initially, improved to 200 hours by war's end, but still poor compared to Merlin's 500-hour intervals. The Americans had accepted reliability penalties that British operational doctrine couldn't tolerate. Yet the strategic impact was undeniable. B-29s delivered atomic bombs to Hiroshima and Nagasaki, ending the war instantly. Conventional incendiary campaigns destroyed Japan's industrial capacity. The submarine blockade starved the home islands. Japan surrendered unconditionally without invasion, saving potentially millions of lives on both sides. The R-3350, despite its flaws, achieved strategic objectives that justified developmental costs. Dr. Carstairs published a comprehensive paper on high-temperature alloys in 1946, incorporating lessons from American and British wartime development. Her research, building on data shared generously by Wright aeronautical metallurgists, advanced understanding of material science significantly. She acknowledged explicitly how American industrial-scale experimentation had validated theories that British laboratories couldn't test adequately due to resource constraints. The personal toll was less measurable, but equally real. Hartley returned home to Yorkshire in August 1945, reuniting with his family after years of separation. His daughter was 12 now, barely recognizing the exhausted man who'd missed her childhood. His marriage required rebuilding intimacy, destroyed by prolonged absence and mutual trauma. He'd aged a decade during 6 years, his hands permanently trembling from machinery vibration, his hearing damaged irreparably. The human cost extended throughout British aviation industry. Workers who'd maintained impossible production schedules for 6 years faced unemployment as factories demobilized. Women who'd mastered precision machining were dismissed, expected to resume domestic roles. The collective trauma of 60,000 British civilians killed by bombing, cities destroyed, families shattered, would echo through generations. But they'd won. The collective engineering effort of Allied nations, combining British ingenuity with American industrial might, had produced weapons that defeated enemies possessing initial technological advantages. The collaboration, though imperfect and often frustrated by cultural differences, demonstrated what Allied democracies could achieve when survival demanded unprecedented cooperation. The R-3350 entered post-war service powering civilian aircraft like the Boeing Stratocruiser. Its reliability gradually improved through peacetime development that war hadn't permitted. British engineers incorporated lessons learned into post-war projects like the Bristol Centaurus, achieving 2,500 horsepower through designs that balanced American ambition with British attention to reliability. Hartley retired from Rolls-Royce in 1956, his contributions acknowledged with an OBE that barely reflected his wartime achievements. He spent retirement years consulting occasionally, teaching at Derby Technical College, writing memoirs that remained unpublished until historians rediscovered them decades later. His story represented thousands of British engineers who'd performed quiet miracles under impossible pressure, whose names appeared on no medals, but whose work was foundational to victory. The declassification of technical documents in the 1970s revealed how extensively British and American engineers had collaborated despite surface-level rivalry. Shared research, exchanged personnel, combined testing facilities, freely given technical advice. The partnership was deep and genuine. British engineers hadn't merely declared the R3350 unfeasible. They'd contributed theoretical foundation and practical wisdom that helped American engineers succeed. The lesson transcended engineering. Britain and America approached problems differently, constrained by different resources and cultural philosophies. British pragmatism emphasized working within limits cleverly. American optimism emphasized overcoming limits through resource application. Neither alone would have won the war. Together, compensating for each other's weaknesses, they'd achieved what neither could accomplish independently. Hartley died peacefully in 1978, aged 76. His obituary in the Derby Telegraph mentioned his Rolls-Royce career briefly, focusing instead on his service as local councillor and church warden. The R3350 that he'd once declared impossible was by then historical curiosity, superseded by jet engines that would have seemed equally fantastical in 1940. But the principle endured. Human ingenuity, given sufficient motivation and resources, can achieve goals that careful analysis deems impossible. British engineers weren't wrong. They correctly assessed their constraints. American engineers weren't reckless. They leveraged advantages that Britain lacked. Together, they demonstrated that Allied cooperation, combining different strengths and compensating for different weaknesses, could accomplish transformative goals that neither partner could achieve alone. That lesson, purchased through 6 years of desperate struggle and paid for with countless lives, remained the war's most valuable engineering legacy. The story of wartime engineering collaboration reveals history's hidden dimensions, where practical British caution met American industrial ambition, forging weapons that won the war. If you found this exploration of the R3350's development fascinating, please subscribe to this channel for more untold stories of ingenuity under pressure. Share your thoughts in the comments. What other Anglo-American collaborations shaped the war's outcome? Ring the notification bell to join our community exploring history's engineering marvels. Thank you for watching.